All right, class, here is the last section of this chapter 1. So, one more differentiation rule. So we've learned definitely the power rule is going to be the most powerful one. Then we've learned how to take derivatives of products, quotients, sums, differences, even to take higher order derivatives. But look at this function right here. How would we take the derivative of this function? Now, sometimes we were able to avoid the product rule by simply multiplying everything out. If I were to multiply all this out, well, that simply means I'm going to need to distribute this parentheses to itself 10 times, yes? And that's going to take a long time, and I'm in no mood for it, okay? Now, fine, don't multiply it out, then obviously then what? You're going to have to use the product rule. So what's going to be the derivative of this? It's going to be the derivative of the first parentheses, yes, times the other 9, yes, plus the derivative of the second parentheses times the other 9, and so on and so on. Then multiply it all out, distribute, combining like terms. That's way too much work, even worse, okay? So, apparently, we can get by really fast. In fact, it's going to take a few seconds for this. And we're going to use the chain rule. So what we have up here is the composition of two functions. So what was the composition of two functions? We're just going to review this a little bit from algebra. Okay. So it says right there, I copied the definition from a book. It says when the output of one function is used as the input of another, we call the entire operation a composition of functions. Usually what we also write, remember that little circle sign? That's how you write composition of functions. And what does it mean? It simply means that the function g is acting on x first, and then the function f is acting on the output of that function, right? So f of g of x. So g does whatever the function g does to x first, and then comes the function f, right? And does whatever it does, but to the result, right? To what comes out of g of x. So basically, a composition of two functions is two functions working in a row on that x, okay? So you've learned about this. Now, as you see, what could be a composition of two functions, like I wrote it, in fact, right here. If I'm looking back up here at this function f of x is equal to, which ones are the two functions composed in here? So I don't want to call it f of x is f of g. So again, I need to do different functions. So that's why I wrote, let's say this function f is the composition of two different functions, g and h. So if I write it as g composed with h of x, which by the way is what? G of h of x is always in this order. So in other words, h is acting on x first, and then comes g and is acting on that result, okay? So if you're looking at this, let's start with the inside function. The h of x, yes, is the inside function. So what's the inside function here? The inside function, in other words, what's happening to x first, I actually have it here. What's happening to x first is this linear function, yes, 2x plus 7. Now once this is done, what does the function g only do? This has already happened, right? You took the x, multiplied it by 2, and added 7. What does the function g do? It takes whatever comes its way and raises it to the 10th power. So these are the two functions that are chained in here. So again, g composed with with h of x is g of h of x. So what's h of x? H of x is 2x plus 7. That's what it equals to. What's g of x? G of x is x to the 10th, but it's not an x that I'm plugging in, right? My x has a new name, is 2x plus 7. So what happens to that 2x plus 7? Well, the function g raises anything that comes its way to the 10th power, right? So as you see, too many circles, but there you go, I'll write it one more time. Composed, chained together, put together, this creates the whole function f of x. So what we need to simply do is look at this function f of x as the composition of two very simple functions. So by the way, if I were to ask you to take the derivative of this h of x, could you do that? Easily. If I were to ask you to take the derivative of this g of x function, could you do that? Yes. So by decomposing the function f, what we're doing is we are breaking it apart into two very simple functions. Okay, so let's try this again. Here's a function f of x. Can you write this f of x as the composition of two functions, g of h of x? Okay, so what would be the two functions that are linked or chained together? What's on the inside? What's this h of x? Well, I could easily say that h of x is the 5 minus x squared. That looks pretty simple, right? Okay, so that's the inside function. Now, when this happened, the g of x comes and does the rest. And what is the rest of it? The rest of it is a 3 plus a square root of whatever comes its way, right? So that's what the function g is doing. So once you're done with 5 minus x squared, you're done with that, right? What else does the function do, the function g do? It has a 3 plus a square root, right? So that's what it does, a 3 plus a square root of whatever comes its way. And because I put an x in here, what comes its way is an x. Okay, this silly ant wants to learn some business calculus, but that's crazy. All right, so we put it together. Could you have done something else? Yeah. In other words, what? I could have said, let h of x just be x squared. That's a simple function, basic function. So this is all I'm taking care of. So that means what? What's left for the function g to do is to do what? The 3 plus the square root, the 5, and the minus, and I took care of the x squared. So that's already done. Okay. This, I think, is better. Okay. So one more time, try this, and again, you could have different answers. You could break it up differently. This function f of x, how could you write it as the composition of two functions g of h of x? So who is the inside h of x? What did you choose? And what's left over for the function g to do? So maybe you chose the h of x to be the x plus 2 parentheses, the adding of the 2. Now what's left for the function g to do? The 4 over, and then the squaring part, okay? The x plus 2 is already taken care of. So when you combine them, this goes in here in place of x, right? Perfectly. What would be a different way? Maybe you let h of x do a little bit more than just plus 2. Maybe you let the h of x be x plus 2 and the square, right? So really kind of two things. If anything, this is a composition of three functions here. I'll tell you in a second. Then if the h took care of the squaring part as well, what does the function g still have to take care of? The 4 over, right? So the reciprocal part, okay? So why is this the composition of three functions, really? Because this is what it is, the plus 2 operation, yes, the squaring part, and then the reciprocal part. So you could make it the composition of three functions. Okay, so all I wanted to do for now is for you to be able to visualize or be able to take a function that's complicated, that's chained in together from more operations, right? More functions, and then piece those apart. Okay. Now, how does the chain rule work? It's pretty simple. So, let's look at the composition of two functions, really f of g of x. Let's go back to the f of g of x function. So f and g are differentiable functions. We'll talk about what it means to be differentiable actually at the end of this section, but clearly differentiable means that you can find its derivative, yes? So you can take its derivative. Believe it or not, as I said, you can't take derivatives of any function. So y is an f of u is g of x. So in other words, what? F is a function of u, and u in turn is g of x. So this is the composition of these two functions, where g is acting on x first, and then comes the function f and is acting on the result. So the chain rule is pretty simple, and what you simply have to think about here is really just multiplying an extra factor. So here it is. In other words, what? The derivative of this function, right, of the composition, let's call it y. So the derivative of y with respect to x, yes, it says it's dy du times du dx. So really what we're doing is we adding in this extra factor of the u, which I can cross out just easily back. So I multiplied and divided easily by this du, right? So it's almost like 2 divided by 3 is the same thing as what? 2 divided by 5 times 5 divided by 3, yes? So I just filled in another factor there. Okay, all right. However, when you look at this, what does that really look like? The derivative of y with respect to u, that's just the derivative of this function with respect to g of x, right? That's what u is. Times, so that's again back in Newton notation. Du dx, so the derivative of u with respect to x, that's just your derivative of g of x. So this is the derivative of the composition of two functions. I'm going to write it again in a minute. But what I'm telling you is that to take the derivative of a composition all the way with respect to x, what you're going to do is take the derivative with respect to the inside function first times the derivative of the inside function with respect to x. So I'm going to write this. So take the derivative of y, which is the composition, with respect to u, and what's u? The inside function, times the derivative of u, which is the inside function, with respect to x. Okay? All right. So, yeah. So again, as I said, notice that the du's cancel out, right? So that's the advantage of Leibniz notation. It actually shows you that it's a product, right? It's a quotient. Each derivative is a change. It's a rate and change in the y values with respect to the x values, right? And in this case, the x values of the function are this output, and the x values of g are just x. So here is the chain rule using prime notation. I'm going to write it one more time for you. So if you have the composition of two functions, and you want to take the derivative of that, I'm just going to rewrite one more time what does the composition of two functions look like. So it looks like this. So f of g of x. So you have an inside function and then another function on top of that. So the derivative of a composition of two functions is, you start by taking the derivative of the outside function, that's f, leave the inside function alone, times move on and take the derivative of the inside function. That's exactly what I wrote there. Okay. So let me write this down. Take the derivative of the outside function leave the inside alone, fine as it is, times the derivative of the inside function. Okay. Oops. There you go. All right. So here it is. Now let's see how this works. So I want you to find the derivatives of these functions. And again, as always, don't forget, write down that you're just about to find the derivative. So this being the function f of x, what is its derivative? So we already pieced this together into two functions. That's your inside function, that's your outside function. So what we said is start on the outside, right? That's your 10 here. So that means what? So the derivative of this is, what's the derivative of something to the power of 10? Is 10 times that something to the power of 9. So what I'm saying is leave the inside alone. All you did is you took care of that outside exponent. So the derivative of anything to the power of 10 is 10 times that something to the power of 9. Leave the inside alone. Times, that's a common mistake, students will put a plus there, it's a times. Now that you did take care of the 10, move on and take care of the inside function. So what's the derivative of the inside function? Well, that's just the 2. Done. So sure enough, 10 times 2 is easy to multiply. That's a 20 times 2x plus 7 to the power of 9. Done. Ta-da. That's what it turns out to be. Okay. Let's take care of this problem. Now, before I'm going to solve that problem, what I definitely need to do is rewrite that radical. Remember, we do not know how to take derivatives of radicals, but what we've learned to do is that we could write them as 1/2 exponent. So what I've done is I've just rewrote my function so that I can now take its derivative. Okay, so what's the derivative of this? Well, what I'm seeing here is the sum of two terms. So when I take the derivative of a sum, I go term by term. So what's the derivative of 3? That would be 0. I'll write it down just so you know where the 3 went. It turned into 0. Plus, this is the part where I actually have two things chained together. So I have an inside function and an outside function. I'm going to take care of the outside function first. So I'm going to take the derivative of a 1/2 exponent. And that would be 1/2 times, leave the inside alone, to the power of 1 less than 1/2. So 1/2 minus 1 is negative 1/2. We're not done. That's just taking care of the 1/2 exponent. I have to say times the derivative of the inside. What's the derivative of the inside part, right? So now I'm looking at 5 minus x squared. So the derivative of 5 is 0, and the derivative of negative x squared is a negative 2x to the power of 1. I have to fix this. So what do I have to fix? First of all, well, that's not going to be there anymore, but 1/2 times negative 2 is negative 1x. I'll put the x to the front. What else is happening here? I have a negative exponent. I should not be leaving negative exponents in my answer. So that's going to, what happens to the negative exponent part? anything that has a negative exponent has to move in the denominator. So that means I'm going to throw this 5 minus x squared under the x, right, in the denominator of this fraction. Then it can get a positive exponent. Okay. All right, and finally, same thing here. Yes, we can deal with fractions because we learn about the quotient rule. But if I could avoid using the quotient rule, I definitely will. And there is me avoiding the quotient rule. Okay. By the way, you should go back to section 1.5. There was a problem that we did there where we actually had to distribute for a second derivative, where we actually had to distribute this out. And I said that once we get to 1.6, you will have learned a new trick and you will be able to deal with it much faster. Okay, oops. So I was going to keep the function in black so I can write the derivatives in blue. Okay, there it is. So I changed this to f just to keep it consistent. So the derivative of this function f of x is going to be, remember, that's a constant coefficient product or a constant product. So there's a coefficient of 4. In other words, we're keeping the constant factor there. Yes, so keep the 4 times. Move on here. And this is a composition of two functions. Now, I'm going to take care of this negative 2 exponent first. So again, how does the power rule work? You take the exponent up front and then you decrease it by 1. And then remember, you leave the inside alone at first. Times, move on and take the derivative of the inside of this parentheses. What's the derivative though of x plus 2? The derivative of x is 1 and the derivative of 2 is 0. So that's just the 1. Okay, so now let's put this together. What do I have? I have a 4 times a negative 2 times a 1. That's a negative 8. And then I have something with a negative exponent. And the part only that has a negative exponent will want a positive exponent. And we can fix that by throwing it in the denominator. So there you have it. Okay. All right, now all we have to do is practice this over and over again. Okay, so let's do this. Let's take care of this derivative. So I'm going to get started. What's the derivative of this polynomial? So that's going to be a 3 times. Again, because it's a sum of terms, we're going to go one by one. Yes. So the derivative of the first term is 3 times 5x to the 4th plus the derivative of 7x is 7 minus, here comes the trouble. This part here alone is a composition of two functions. So how do I take the derivative of the composition? Remember, you start with the outside exponent. So the derivative of 7 times, or anything to the power of 7, yes? Bring down the 7, decrease the power by 1. Leave the inside alone. But you're not done, yes? Times, go on and take the derivative of the inside function. So the derivative of x squared is just the 2x. Okay, so let's see if we can simplify this a bit. I'm going to get a 15x to the 4th plus 7. And then the thing is 7 times 2, that's a 14. And you can even throw the x in the front of the parentheses. And there it is. Definitely I'm not going to distribute this up because how? I would have to raise it to the 6th power first, right? Remember exponents before multiplication? So there's no way I'm going to want to multiply all this out, right? Same as I didn't want to multiply these 7 factors out. Okay. So we'll take a break for now. And then we're going to continue on the next video.